Now, the normal force is a very special type of reactive force. It depends on what your object is doing. And we're going to do a couple of different examples with it. So let's take the case of you have a box, which is here on your screen, sitting on a flat surface. If this box is sitting here on Earth's surface, it's going to get pulled down by gravity, much like if you were to put this box on a table. Now, this force of gravity is pulling it downwards, and you can test this by lifting an object above the table and letting it go. It'll fall. However, when it's sitting on the table, it doesn't go anywhere. If it's not going anywhere, this means that the net force is zero. And this, therefore, requires there to be a second force that is 72 newtons upward in order to cancel out the downward one. This force here, which is required so that our box doesn't pass through the surface, is referred to as the normal force. The reason why it's called the normal force is normal means perpendicular to the surface. So here you'll see that the surface is horizontal, and the normal force thus will be vertical. Right? So whenever you have a normal force, it'll be perpendicular to the surface. Now this is probably the easiest case of the normal force, but keep in mind some people in the past have liked to say that the normal force simply opposes things like gravity. That's not necessarily true. It only opposes forces that try to make your objects pass through one another. And it's possible to break this assumption of the normal force. If you take a sledgehammer and smash it into your desk, it's possible for your sledgehammer to go through the desk when provided with enough force. But basically, if we assume that our things don't pass through each other, the normal force will cancel out whatever force is pushed downwards onto it. And this also extends to applied forces. So instead of the force of gravity, let's say we were to push down on this box ourselves. So we're going to give it an applied force of, say, 10 newtons downward. Our normal force would actually adjust to this additional 10 newtons. If our net force is 0, because our object can't pass through one another, by pushing down on the box or adding this applied force, we would actually change the normal force required to cancel it out. This is why the normal force is reactive. It reacts to what you do. Now, this is a case, or this is basically a linear case in which we're just going up and down. You can actually further exemplify this by moving to a diagonal case. So in the diagonal case, we can tilt our surface so that it's at an angle above the horizontal. And what you'll notice here is that the gravitational force still pulls it downwards. If this is the case, you might ask yourself, well, what normal force are we going to have? At the end of the day, even though the force of gravity is straight downward, the normal force only prevents this box from passing through the surface. It does nothing to stop it sliding up and down the surface. Thus, if we were to look at our normal force here, it again is going to be perpendicular to the surface. In other words, it only cares about canceling out the part that is along the normal or perpendicular to the surface. It doesn't care about any part of the force that is going up or down the ramp. This is why if you place an object onto a surface and you tilt the surface up at an angle, it actually slides. It's sliding due to gravity, but the reason why it slides when it's at an angle is because the normal force only cancels out part of the force of gravity. So for example, if you take the force of gravity here, you can do this with any vector. You can split the force of gravity up into two parts. One that is along the surface of the ramp, and one that is directly perpendicular or normal to the ramp. The only one the normal force cares about canceling out is this one here. Whatever component of the gravitational force that would be along the surface, it doesn't do anything about it. Now, with that being said, in this particular case, well, how are you going to determine this? Well, at the end of the day, there's a couple of ways that you can do this. In the simplest case, you can use trigonometry. If we have the angle of the ramp here, you can use a method of similar triangles. You'll find that this angle is the same in this particular triangle. And thus you can use sine and cosine to find the part that's down the ramp and the part that's into the ramp, because the hypotenuse is 72 newtons. As such, your normal force here will be upwards, but it will basically be equal to y. That's one way of doing it. However, when you're moving to multiple dimensions, for example, 3 dimensions, this becomes significantly harder to do. Because number one, you need to be able to draw it. Number two, you need to be able to figure out, for example, that these two angles are related. Right? So you need to be able to use methods of similar triangles to relate angles that are the same. This is where one of the specialized tools that we discussed with previously in the class actually comes into play. At the end of the day, what we're doing here is we're taking the force of gravity and we are finding the part of it that points along a particular direction. So if you want to do this efficiently, we have a particular tool for this, known as a vector projection. This works for splitting up any force or any vector quantity into any arbitrary direction. So if you want to cancel out or find the normal force, what you need to do here is you're going to use the force of gravity, because that's where your force is ultimately coming from, and you're going to use the normal direction, which is a unit vector perpendicular to the ramp in place of b hat here. And if you do this, this AB will give you y as a vector directly. Because what it does is it finds the part of the force of gravity that points in any arbitrary direction that you want. Alternatively, if you wanted to find, say, x, so we'll do it in blue, you would still use or find the part of the force of gravity, but you would change the direction to be, say, down the ramp. And you would use this for your hatted quantity. And that would allow you to find the part of the force of gravity that points down the ramp. So this vector projection tool will work in any situation. The minute you know which direction you want to find the component of the forces, all you need to do is apply this equation directly. It has one job, and that's all there is to it. Now to do so, you need to be able to find a unit vector and perform a scalar product. And what you'll find is one of the problems in this section is designed to see if you can do just that.